Bismillahirrahmanirrahim. Assalamu alaikum. This is Dr. Bassam Mohammed with you, CHENG324 Process Modeling and Simulation. Today we'll be taking lecture number 21 and we are going to continue solving problems from chapter number 5. So we solved last time 5.2, 5.3, 5.4 and 5.5. So we are going to continue now with 5.6. Okay, so we are going to continue with 5.6. So looking at 5.6, the question says the overall transfer function of a process given by G is equal to G1 by G2. So here we are talking about two transfer functions in series. And if you have two transfer functions in series, you multiply them. And actually two functions in series, it also looks like that you are having like two tanks. They are in series, and there are many examples to have things in series. Okay, so this is the transfer function where G1 is equal to a normal transfer function, first order, and another the second one is also first order. We have the values of tau 1 and tau 2. Okay, so what is the overall gain? So that's the first part of the question, which is just the multiplication, which is K1 multiplied by K2. That's the overall gain. For first order system, the time constant is the time for a step change when y reaches 63.2% of the steady state is the equivalent time constant for the step response of the second order system G reach time when the response reaches 63.2%. We know that for first order, tau is reaching 63.2% of the change of Kn, right? So now, is that also applicable if you have a second order system where we can say that tau 1 and tau 2 of the second order system, we just can add them and they will add to the 63.2%? Is that true or not? Show supporting calculations for the step response formula given to us. So this is the formula given to us if you do the Laplace, you will do the partial fractioning and then doing the Laplace inverse. Can y of t show oscillations for a step input? Of course, we said that anything that would show an oscillation should have a complex root in its denominators, the zeros of the denominators, which we do call the poles. Okay, that's all now. So let's go and start solving the problem. So for 5.6, what do we have? We have the transfer function of the first. Let me put the transfer functions that we said that both of them, they look like two transfer functions in series, G1 and G2, and that means that if you want to find the relationship of the input with the output, x of y of s to the input x of s, this will be output over input is equal to G1 over G2, and you just multiply the transfer function of both of them and you will get, of course, the K1 multiplied by K2 over tau 1 s plus 1 into tau 2 s plus 1, and here that is called the overall gain. Okay, so that is the overall gain that we have, and here is tau 1 and tau 2, the time constants. Okay, so part A, what is the overall gain? The overall gain is equal to K1 multiplied by K2. Okay, so that's the first part, and then the second part, if the equivalent time is equal to tau 1 plus tau 2, which is equal to 8. So tau 1 is given to us, which is 5, and tau 2 is given to us as 3. So now if you want to add tau 1 plus tau 2 is equal to 8. 8. So is that very equal to that this achieves 63.2%? We know that now if we are talking that this is the time constant and this causes 63.2% of Kn, which means that for a first order process, for y at t is equal to 8, we know that y divided by y infinity or Kn, okay, is equal to 0.632. We showed this by another way by saying that at y at t is equal to 1 tau, you're going to have 63.2% of km. Okay, and in this case my tau is 8. Okay, and I just want to make sure is that applicable or not. That is for a first order. However, for the second order, it was given to me that y divided by km is equal to, I don't know if you can see the equation just to make sure. So here's y and here's km. Okay, so y divided by km is that equation here. So 1 minus after the substitution, e to the power minus 8 over 5 minus 3 e to the power minus 8 over 3 over 5 minus 3. After substitution, we will see that this is equal to 5.599, which is not equal to 2.632. So that is not applicable. It's very close, but it's not applicable. It's not applicable. So we decide that therefore the equivalent time constant is not equal to tau 1 plus tau 2. Okay, so it's not equal. Well, now part C tells me that if it is oscillatory or not, and we said that to know that it is oscillatory, you look at the zeros of the denominator, and looking at the zeros of the denominator, in which we already called those as poles, and we said that to have them oscillatory, that means the poles should be complex roots. Okay, should have complex roots. Okay, should have complex roots. Okay, do they have complex roots? I don't know. Let's check. Okay, and if we check the roots of the denominator, the roots of the denominator that we have, what is the denominator? If you just can remember the transfer function that we have, it is k1 into k2 over tau 1 s plus 1 into tau 2 s plus 1. So by looking at the denominator here, we have tau 1 s plus 1 is equal to 0, so s1 is equal to minus 1 over tau 1, and tau 2 s plus 1 is equal to 0, so s2 is equal to minus 1 over tau 2. We can see that both are negative real roots, which definitely means that they are stable. It means that they are stable, and we are going to say that and not oscillatory. Okay, and not oscillatory. It will not be oscillatory because it has no complex roots. Okay, so definitely it will not be oscillatory. And actually, if you look at this for a moment, if you try to analyze it and do the partial fraction, okay, you do the partial fraction, this will be a over tau 1 s plus 1 plus b over tau 2 s plus 1. And by taking the Laplace inverse, okay, so here's the partial decomposition, okay, and here by taking the Laplace inverse, the answer would be a into, this is like 1 over s plus a. You need to fix that to be 1 over s plus a. So before I take the Laplace inverse, I'm just going to fix it a little bit, so that a over tau 1 over s plus 1 over tau 1 plus b over tau 2 over s plus 1 over tau 2. And now it's ready to do my Laplace inverse, and taking the Laplace inverse, this will be a over tau 1 taking out as a constant, and 1 over s plus a, it will be e to the power minus t a to the power minus 80, right? 80 in this case, my a is 1 over tau 1, so this would be like t over tau 1 plus b over tau 2 into e to the power minus t over tau 2. Okay, so we already can see that we have two exponential terms. This is also why I said that's stable, because the exponential terms are two negative values, and we don't have any sine and cosine. We already know that because I know that I don't have any complex roots. Okay, so that is for 5.6. Okay, so that is for 5.6, and I think so now we can look at 5.7. Okay, Oh, okay. We'll not solve 5.7 because it's a bit very long. I'm not sure. Should I solve it or not? I would like to keep that to you if you would like to solve it. It's not that difficult. It's just that I'll try to solve the things which are easily to grasp and helps you to build your basis of understanding. Okay, so for 5.8, so solving 5.8, we are going to solve 5.8, and here's 5.8, and 5.8 I have a liquid storage system shown below. The normal operating condition, our Q1 is equal to, and this bar means what? It means steady state, okay? So Q1 bar is equal to 10 feet cube per minute, and Q2 bar is equal to 5 feet cube per minute, and H bar is equal to 4 feet. So I'm going to write these. So Q1 is equal to 10 feet cube per minute, and Q2 is equal to 5 feet cube per minute, and then we have H steady state is equal to 4 feet. And this is of course the initial steady state values for all of them. And this is I usually write steady state. This is the way how I got used to it, but there are many books which they write it as bars. The tank is 6 feet in diameter, and the density of each stream is 60 pounds per feet cube. So 60 feet in diameter. So if I say diameter is equal to 6 feet, I know that the area is going to be the cross-sectional area for that tank, which is pi 6 square over 4, right? And what else do we have? We have also the density is 60 pounds per feet cube, okay? 60 pounds per feet cube. I think so we had good information here. We can't find anything. Suppose that a pulse change is in Q1 occurs as shown in figure E 5.8. Okay, so we are going to look at the pulse, and then what is the transfer function relating H prime to Q1, H prime to Q1. So let's just see the system. So this is the system that I have here. Okay, so this is the system, and in that system I have Q1 and Q2, and the exit is Q, and we can see that there is a pump here. So that means Q does not depend on the head pressure, and this is like an integrating process, because if you have any change in Q1 that increases, this will not be affected by H if it increases, so it will increase till it overflows. And if you look at the input is changing for Q1 from 10, the initial steady state value for Q1, to 15, which is 5 over S, and then it goes down minus 5 over S. That happens at 12, which is e to the power minus 12s. Okay, so what do I have here now? I already know. I want to find the relationship between the height. I want height with Q1. Okay, height with Q1, and that is my problem here. If you look at my tank here, in which I have Q1 and Q2, and then I have a pump here, which is Q. Okay. So I have Q1, Q2, and a Q. Just to make sure that I have this right, Q1, Q2, Q. Yep, I have it right, and I want to see, look at the height. Okay, so looking at that, and Q is the volumetric flow rate. Okay, so if you remember the equation, dm by dt is equal to input minus the output. And for dm by dt, this is equal to rho a into dh by dt, considering that, of course, density is constant. I'm assuming that, and we know that area is constant. So this is like given, or we know it, all right? And this is just like an assumption. Okay, and so the input flow rate here, in this case, of course, dm by dt is equal to mn, and mn I have rho n fn. The system he's using here Q1, so I'm going to use the rho Q1. Okay, so to be rho Q1 plus Q2, these are the two inputs, minus Q, which is the output, and of course I can cancel out the density terms, and I'm going to have my equation that looks like that. dH by dt is equal to Q1, okay, Q1 plus Q2 minus Q divided by area. So that is my equation here. I want to find the relationship between H and Q. So this is the way how I'm going to start linearizing and doing the deviation format, where dH prime of dF by dt is a function of the state variable, and the state variable here is H, and the rest, if we can see the rest of inputs, are Q1 and Q2, and Q now is also part of an input factor, as a part of an input factor as well, because it is related to the pump and it does not depend on the head pressure. Okay, so this dH prime by dt is equal to dF by dH, okay, dH into H prime plus dF by dQ1 into Q1 prime plus dF by dQ2 into Q2 prime plus dF by dQ into Q prime. Okay, so these are the this is the equation that I have here. And if you take now the partial differential equations, and all of them will look similar, so dF by dH, it's only dF by dH, there's no dF, there's no H in this term here, so it will be 0. Other than that, dF by dQ1, it will be 1 over area for all of them. So this will be like, this is 0 plus 1 over area into Q1 prime plus 1 over area into Q2 prime plus 1 over area into Q prime. And this is equal to dH prime by dt. Here, since we want to find the relationship, and we said that before, we want to find the relationship between what? Between H and Q and Q1. So we will set other input variables as 0. Other input variable deviations, it's not setting them to 0, so the deviations are not changing, so they're like as set as 0, which includes what? Which includes, in this case, Q2 and Q. And in this case, I'm going to have just dH prime. I'm going to concentrate on the other terms here, and I'll take directly the Laplace. So this will be SH of S is equal to 1 over area into Q1 S, and the others are not going to be considered. So if I want to find HS over Q1 S, this will be 1 over area S. And this is what we call as an integrating process, and I already said that because we have a pump at the output. So this is an integrating process. An integrating process, that means it will increase always if we have any step input that is increasing, or it will empty if you have a step input which is decreasing. Okay, so this is what we have. This is what we have as an equation. And now our second part of the question is asking us if the second part of the question is asking us derive an expression for h of t for this input change. Okay, so if we have an input change of 5 over s minus 5 over s e to the power minus 12s, what will be the output? So if I have my input change, which is equal to 5 over s minus 5 over s e to the power minus 12s, what will be h of s? So I'm going to substitute that. So this will be 5 over s minus 5 over s e to the power minus 12s, and this is multiplied by 1 over as. Okay, now after doing this multiplication here, it doesn't look like straightforward, but we need to just multiply. So this will be 5 over a s squared, so it's like 1 over s squared, minus 5 over a s squared, again 1 over s squared, e to the power minus 12s, and taking now the Laplace inverse, we are going to get 1 over s squared, which is t, so it's like 5 over a t. Okay, so it's like 5 over a t, minus 5 over a minus 5 over a t. However, here's t minus 12. Okay, t minus 12, which means that this happens when it will happen at 12 seconds. The second part will happen at 1 second, right? Great. So that is what? That is the answer for h prime of t. H prime of t. So this is the equation that we have. I don't know if it is asking for more than that. What is the new steady state value of the liquid level? Because of that, because it returns to its condition, because it returns back its condition. So there was an effect, but the effect was removed, right? The vector was removed. So what will be the answer in this case? And the effect was removed when? It was removed at 12 seconds. So what will be the effect? Actually, this is tricky. Okay, so what we are going to do now, okay, so we know that at t is equal to 12, which is t is greater or equal to 12, it will not be changing. It will, because what happens if you change q1, and this is q1, and because of this change, this will increase, and as you go on the negative side of q1, this will not decrease because you are returning just to your condition, and because this is a pump, it will not be affected by any change in q1, which means that if you substitute t is greater than 12, which is 12 is good enough to substitute for that. If you want to substitute higher, you're going to find that you will also get the same answer, okay? And by area, which is pi d square over 4, so you substitute those values and you'll find out that my h prime of t, it is equal to, what was the initial height? I forgot actually. 4 feet. 4 feet. No, that was the, yeah, it's also 4 feet. Okay, so this is equal to 2.122, and if I want to find h, okay, if I want to find h, that will be 2.122 plus 4, so it will be 6.122 feet. So that is the new steady state value that we have. That's the new steady state value. I think so this is good enough, because here it wants us to repeat just B and C for the doubled 2 pulse inputs, and I'm not going to go through that. So this is good enough to solve 5.8. That's 5.8, and looking forward to also to solve the next question. Okay, so we are going to continue to solve problem 5.9. So here's 5.9, 2 liquid storage systems shown figure E 5.9, and here's 5.9. I think so I solved something very similar to that, but that's okay. So I have like 2 systems, one which has a valve at the output and the other one which has a pump at the output, and it's telling me that each tank is 4 feet in diameter. For system 1, the valve acts as a linear resistance with the flow head relationship. So instead of saying F is equal to alpha square root of H, so here we are saying that it's not to the square root. So it's not the square root of H, it is linearly proportional to the height, and this is the value of alpha. We're using gallons per minute and H is in feet. For system 2 variations liquid level, H do not affect exit flow rate. So definitely for the second one, it's saying that this H does not affect the exit flow rate, because the flow rate depends on the power of the pump. Depends on the power of pump. Whatever the height is going to go up or down, you'll always have a fixed output here. Okay, so what's the problem? We do have the steady state value at 6 feet and QI input flow rate as 50 gallons per minute, and that at time is equal to 0. The inlet flow rate suddenly changes from 50 to 70. So initially it was at 50, and then it went from 50 to 70, which means that I'm having a step input of 50 to 70. That is 20 over S, right? Okay, and for each system, determine the following information: the transfer function for H with QI, and the first one is going to be exponential term, the second one is going to be an integrator, What the prime denotes deviation variables, we know that. The transient response, we want h of t. And then the new steady state levels. So that is using the final value theorem, I can find the new steady state values. If each tank is 8 feet tall, which tank overflows first? Okay, that's nice to look at. We can't answer now. We will answer later when we solve the problem. Okay, so talking about 5.9, we already know that we have two tanks. So talking about system 1, okay, talking about system 1, if you can recall, dm by dt is equal to mn minus m out, and working on that, we have the rho is going to be cancelling out, so we have a dh by dt is equal to, I already cancelled the rho, this is minus, not alpha square root of h, is also already given to us, it's 8.33h. Okay, and just continuing on to solve the problem. Here we have the FIs in gallons per minute. So if you want to change gallons per minute to feet cube per minute, so there's a conversion factor to do that, and we are going to do this conversion factor in a moment. Okay, so all what you need to do here is take not Laplace. Actually, we can't take something like Laplace here because this is already like in linear format, right? So if you take the steady state, I'm going to do the normal way of doing the first methodology that I was mentioning, and here this will be directly like a dh prime by dt, right, is equal to fi prime minus 8.33 into h prime, and doing my Laplace, I will have this to be appearing something like that. Okay, and this is now all without doing the conversion factor, so I'm going to continue on because you just need to multiply the q with the conversion factor. Okay, I forgot the a? Yes, again I forgot the a that I have here. Okay, and I kept here fi. I know it is using qi, so if you want to put qi, so I think so we'll put qi. So rather than going through the whole of the top, you already know what's going on. So I'll just put this at qi, and this is in gallons per minute. So what I need to do, I'm going to multiply it by the conversion factor, which is 0.1337, and this is also in gallons per minute. This was q. Remember, this was q. So we will also multiply it by 0.1337. So this is just a conversion factor to work on it. Okay, so since we have done our Laplace, all what we need is to do some kind of an arrangement, and this arrangement will result in this transfer function. Okay, so I just did it quickly because this is straightforward of what we have taken before. So this is what we have here. If we are talking about tank 2, it is different. Okay, so tank 2 is a dh by dt again is equal to qi minus q. This time q is it is like a constant output flow rate that does not depend on the height. And if you continue with the problem, this will be like, again, if you do the dh prime, you will find out that this will be directly something like that. And then you will do your, of course I want to multiply this by the conversion factor just to turn it to feet cube per minute, and then take the Laplace. And doing the Laplace, I'm going to have this is equal to qi, okay, 0.11337 qi, and actually it is qi minus the q term, right? It's also minus the q term, but since we are just looking at the effect of only qi on h, we said that you put the second one like the other thing as a constant, so the deviation is going to be 0. So we are going to have only these first two terms, only these two terms here. So just taking a common factor and then finding the transfer function, it is going to be 0.011 over s. Okay, great. So we obtained the two transfer functions. The two transfer functions we have What we need to do now, it is saying that if we have a step input, so if we have a step input which was from 50 to 70, okay, so that was like our system here. Sorry, that was our system here. It was from 50 to 70, and that is like 20 over S, right? So this is like 20 over S. And doing the step input for our system here. So for tank one, if you can recall, H prime over Qi of S, it was equal to 0.12 over 11.28 S plus 1. So that was the equation, and just taking multiplying it by 20 over S. Okay, so what I'm doing here, I'm substituting Qi and then I'm multiplying it, of course, here. So I have H prime, and this domain will be equal to 2.4 over S over 11.28 S plus 1. This is if I want to do the multiplication, but why should I do the multiplication and then find out the A and B? Okay, so this is if you want to do the fractional decomposing and so on. But what I really like to do is that I already know from this, like this is like a step input to a first order process, and as y of t, this will be km into 1 minus e to the power minus t over tau. So I'll just make my shortcut. So my m is equal to 20. I know m is equal to 20, and my k, let me look at that just to remember. Okay, my k is 0.12. Okay, k is 0.12, and tau is equal to 11.28. So I have all the values that I really need here. So in that case, I'm going to have h of t. I'm going to write that in white. Okay, so that is h of t is equal to km. Km is 20 into 0.12, and that is 2.4 into 1 minus e to the power minus t over tau, and tau is 11.28. Okay, so that is that's the first part. So that is for tank 1. And doing for tank 2, we already know that the transfer function is equal to 0.011 over S, and we know that Qi over S is 20 over S. So this will be H prime is equal to 20 multiplied by 0.0011, that is like 0.22 over S squared, and definitely this is like a ramp, and the H of t, this is H prime of t, sorry, so the H prime of t is equal to 0.22 t. Okay, so if you want to find H of t, I mean, this is just if you want. Okay, so if you want to find H of t, you just add the steady state value. I don't know if you need to do this, but I'll just write this in a small letter. So if you want to find H of t, you're going to say that is H steady state, which we already know that initially it was 6 plus 2.4 into 1 minus e to the power minus over 11.28. Okay, so this is if you want to find H of t, right? And again, if you want to find H of t here, this will be 6 plus 0.22 feet. So it's 0.22 t. And that is the second equation that I have. So I have two equations here. This is the first one here for H of t, and this is the second one for H of t. So these are the two equations that I have. And actually I could have done the final value theorem, but since I already found H of t, I think it's easy to see that. And for the first one here, if t approaches infinity, I can see that this t term I have e to the power minus infinity, so that will be 0, and the answer will be like 6 plus 2.4, which is 8.4 feet. So I can say that if I just go to the side here, so I can say that it is very clear for me that H of t is going to be 8.4 feet. However, this is for tank 1. However, if I'm going to look up for tank 2, if I'm going to look up for tank 2, I can see that I have the t term here, so as t approaches infinity, it's very clear for me that h of t is going to be infinity, right? It is going to be infinity, and that is for part C, in which it just tells me that how do things react. So the first one, it says that it's going to go to a new steady state value. Okay, so it was at 6, and then it went to 8.4 feet, like 8.4 feet. For the second one, it looks like that it just went in this shape. It just went like that, okay, as a ramp. And if you look at how does that look as a tank, okay. So for the tank, for the first one, it increased from one position to a new position, and for the second one, it went to infinity. That means it increased till it started overflowing, right? So that's what we mean by infinity. Great. Now the question is that what's the height of that? What is the height of that tank here? Actually, I didn't see what is the height of that tank here, and I don't know if it's mentioned a certain height for that tank. Okay, so it says here if each tank is 8 feet tall. Okay, so now he's assuming that it's already 8 feet tall. Okay, both of them are 8 feet, and since both of them are 8 feet, that means even this will be overflowing, right? Even this will overflow, and definitely this will overflow. Now, which one will overflow first? So if you substitute h, which is 8, if you substitute h, which is equal to 8, I can calculate the amount of time that it will reach 8. And in this case, I already have the equations. I have the two equations. So that is my first equation, and that is my second equation. And it's substituting the value of h, if 8 feet, or in the value of h, 8 feet, I can calculate what are the values of t. And in this case, I already did that. So for tank 1, you're going to see that this will be my equation. 8 is equal to 6 plus 2.4 to 1 minus e to the power minus t over 11.28, and we are going to find that t is equal to 20.1 minutes. Okay, and for tank 2, we have our equation is 8 is equal to, as you can see here, 6 plus 0.22t, so that is like 6 plus 0.22t at 8 feet, and then you calculate t, and t will be 2 divided by 2.22, which is 9.4 minutes, which means that the tank 2 will overflow first, right? It will overflow first. Why? Because t 9.4 minutes happens before 20.1 minutes. Great. So that was the problem for 5.9. It was actually a very good problem. I liked it, and we gained a lot from that problem. Beautiful, beautiful. So we did solve a good problem here. So what is the next question that we are going to solve? I can see here that the next problems that you're going to solve from probably maybe 512 and 513, and then I'm going to solve 514 as well, 515, 516, yes, 517, we are going to solve all that, and 517, and I think so that will be it. So we are going to solve a group of problems, 517, and then we're going to jump to 520. Okay, we are going to jump to 520. We're going to solve this 520, and that could be it. We may solve 521. We see how that will go. So we have about 6 or 7 problems that we will try to solve next time. Even that 522 is interesting. I'm not sure that you're going to solve this, but that will be a lot. It's like solving all the problems. And most what we are going to be taking from 512 till the end of this chapter 5 will be on second order processes, and this means that I think it's good to stop here because we solved mainly the first order processes, and next time we're going to continue solving chapter 5. However, we are going to solve the solving second order systems, right? Second order systems. So by that, I think so we are done up to here, and see you next time. I feel that we together did a good job here, and if you solve all the problems, I guarantee you, all the problems that we have went through, I guarantee you that you're going to get a really good grade. A good mind of practice, of understanding, of analytical thinking, critically analyzing of what is happening, having a sense of engineer of what you're doing, and reflecting back on your real life, even at your home, with a tank, with a pump, with the florist, with the tap water, and so on. You will get a good grasp of what you're trying to say here. So good luck, all the best, and see you inshallah soon in our next lecture. Ma as-salama.